So, let's talk about electricity. I know, it sounds super intimidating, right? But what if I told you it's not really complex physics, it's more like learning a new language? Seriously, you just need to know a few key words, some basic grammar, and pretty soon you'll be speaking it fluently.
I mean, does looking at a bunch of wires and batteries feel like you're trying to read some ancient forgotten code? Do you hear words like volts, amps, and watts and just tune out? Yeah, if that sounds familiar, you are in exactly the right place.
Because today, that all changes. We're going to crack that code, and we're going to do it together. I promise by the time we're done here, you'll have all the tools you need to understand the basics of pretty much any electrical system out there. So, let's just dive right in.
So here's the game plan. We'll start with the two main types of electricity, AC and DC, and why we need both. Then, we'll get into the vocabulary, volts, amps, and watts. After that, we'll see how they all work together with the power equation. We'll add time into the mix, and then, for the fun part, we'll put it all to work inside a real system.
Okay, first things first. Not all electricity is created equal. It doesn't all flow the same way. You can think of it like two different dialects you need to know: direct current, or DC, and alternating current, AC.
Let's make this easy. Think of DC power like a river. It flows nice and steady, always in one direction, from a positive point to a negative point. This is the kind of power you get from batteries. It's what your phone, your laptop, and most electronics actually use. Now, AC power, that's what comes out of the outlets in your wall. This is more like an ocean wave. See, the water itself doesn't really travel across the ocean. It just moves up and down. But the energy of the wave sure does. AC works the same way. The electrons just kind of wiggle back and forth, and that vibration is a super efficient way to send power over really long distances. It's why our entire grid is built on it.
All right, so we've got the two dialects down. Now it's time to learn the three most important words in our new language of electricity. And to make this really stick, we're going to use the old classic, the water hose analogy.
First up, voltage, or just, volts. This is the water pressure in the hose. Even before you squeeze the handle, that pressure is just sitting there, waiting, right? That's voltage. It's the potential force. So the main thing to remember is that voltage is all about compatibility. A 12-volt appliance absolutely needs a 12-volt power source. It's that simple.
Next, we have amperage, or amps. So if voltage is the pressure, amperage is the actual flow of water. Think of it as how thick the hose is. Now, this is so important. If you try to push a huge amount of flow, a ton of amps, through a tiny little wire, what happens? You get friction, and that friction creates heat. It's dangerous. That's why the number of amps you're dealing with is what tells you how thick your electrical wire needs to be.
And that brings us to the big one, wattage, or watts. This is the total power, the whole shebang. In our analogy, it's the total amount of water you're actually delivering. It's not just the pressure, and it's not just the flow. It's the combination of the two that tells you how much real work is getting done. So we have our three words, volts, amps, and watts. Now we need to learn the grammar that connects them. And trust me, it's the most fundamental rule in this whole language.
That's it. It's really that simple. Pressure times flow equals total power. Volts times amps equals watts. If you only remember one thing from all of this, please make it this right here. This little equation unlocks everything.
Okay, and here's where it gets really cool. Check this out. You can get 10 watts of power with high pressure and just a trickle of flow. That's 10 volts and 1 amp. Or you can get the exact same 10 watts of power with super low pressure but a whole lot of flow, 1 volt and 10 amps. See how they're interchangeable? This trade-off is what makes the whole power grid possible. They use incredibly high voltage so they can move massive amounts of power with very low amps, which means much less heat and wasted energy.
And the best part? You can flip this equation around to figure out stuff you don't know. Let's say you have an appliance, and the label says it uses 120 watts on a 12-volt system. Well, now you can find the amps. Just divide watts by volts. 120 divided by 12, that's 10 amps. Bam! Now you know exactly what size wire and what size fuse you need for it. Super useful.
So far, everything we've talked about has been like a snapshot, power in a single moment. But in the real world, for things like your power bill or charging a battery, what you really care about is how much power you use over time. And that brings us to our next crucial term. And that term is the watt hour. The name pretty much says it all. It's simply the number of watts you're using multiplied by the number of hours you use it for. So if you have a 100-watt light bulb and you leave it on for 10 hours, you've used 1,000 watt-hours of energy. This is the metric for measuring energy storage and use.
So why should you care about watt-hours? Well, for one, your electricity bill is probably measured in kilowatt-hours, which is just 1,000 watt-hours. But maybe more importantly, it's the only real way to accurately compare the capacity of two different batteries. And it's what tells you how long that battery is actually going to run your gear.
And this right here is a really critical point that trips up so many people. It is so tempting to look at two batteries and just compare their amp hours. But that's a trap. A 100 amp hour battery at 12 volts holds literally half the energy of a 100 amp hour battery that runs at 24 volts. The only way to compare them apples to apples is to look at the watt hours. Just remember, volts times amp hours equals watt hours. That is the true, honest measure of capacity.
All right, enough theory. We've learned the language, we've got the vocab, we know the grammar. Let's put it all together and walk through how you'd size a basic solar power system from scratch.
These are the 4 big steps. First, we got to figure out how much energy storage we need in our battery. Second, how many solar panels do we need to fill it up? Third, what size charge controller can handle all that incoming power? And last, but definitely not least, how do we connect it all safely with the right wires and fuses? So let's start with the battery. In this example, we've got 3 12-volt batteries, which gives us a grand total of 5,580 watt-hours of storage. But here's a pro tip for this kind of battery. You really only want to use about half of its total capacity to keep it healthy for a long, long time. If you drain it all the way down, you'll damage it. So that means our actual usable energy each day is half of that total, or 2,790 watt-hours. Okay, next up, we need to charge that battery. We've got 4 solar panels that together make a 404-watt solar array. So how big does our charge controller need to be? Well, let's use our magic equation. We take the total wattage from the panels, 404 watts, and we divide it by our system's voltage, which is 12 volts. That gives us 33.7 amps. So we'll need a charge controller that can handle a bit more than that. A 40-amp controller is perfect, gives us a nice safety margin. See? We just used that simple equation to make a really important practical decision.
And finally, safety. This is non-negotiable. Remember what we said. The more amps you have, the thicker the wire needs to be to prevent overheating. You can easily find charts online to get the exact right size. And the fuse? Think of the fuse as a bodyguard for your whole system. It's a cheap little part that's designed to blow and cut the power if something goes wrong, protecting all your expensive stuff. A great rule of thumb is to pick a fuse that's rated for about 25% more than your device's normal amps. So for something that draws 10 amps, a 12.5 amp fuse is a perfect safe choice. And that's really it. We've gone over AC and DC, the key vocabulary of volts, amps, and watts, the simple little equation that connects them all, and we've even seen how to apply it to a real-world problem. You now speak the language of electricity.
You've cracked the code. The mystery is gone, and what's left is understanding and, well, potential. So the only real question left is, what are you going to build? What are you going to power? That is entirely up to you.